Hello, everyone. My name is Nash Mahmood. I'm an associate professor in computer science and engineering at Louisiana State University. And today I'll be presenting our paper on combining information retrieval methods to improve bug localization. This paper is co-authored by my PhD students, Saket Kariwada and Nurse Latushay. To understand our contribution, let's take a step back and try to understand the life cycle of a software bug. So a software bug goes through into three stages in its life. The first stage is an error, which is a human misunderstanding some specification. Once that error makes its way to the code or the source code, it becomes a fault. Once a fault gets exploited, it becomes a failure. A failure is basically when a departure from the expected behavior of the system. Whenever software systems fail, some sort of a report that is known as the bug report that documents the failure gets prepared and sent to the developer. These reports look something like that. There's some sort of metadata to document the time of the bug and where it happened, and some sort of a textual description that describe what exactly happened. Now, whenever developers get these bug reports, they try to match them with their existing source code base and try to identify the parts of the code that are responsible for the bug or for the failure. This process is known as bug localization. Now, bug localization is a very expensive process. Empirical research has found that close to 70% of developers' time during maintenance sessions goes to basically try to localize bugs. Now, we have two different techniques or methods trying to find bugs in software system or localize bugs in software system. The dynamic versus the static method. Dynamic methods are known to be expensive. The way they work is that you try to run the system and try to regenerate the sequence of actions that led to the error. And based on that, try to identify the part of the system that needs to be fixed. Now, this approach is a little bit expensive because there's no guarantee that you can actually generate the exact sequence that led to the failure. So you have to run the system multiple times before you actually can localize the bugs. Now, we have the static methods, which are known to be cheaper. And the way they're implemented is usually using information retrieval methods. So the IR approach for bug localization can be described as follows. Assuming we have the bug report, which is written in usually plain English language, and we have the source code, an IR method tries to extract the textual components of source code and match them with the textual components of bug reports. Source code files that share a lot of textual similarity with bug reports are highly likely to be related to the bug. So the way this process works is very simple. Assuming we have a bug report, the following bug report, I am unable to log in with valid email and password, please help. And we have the file login.java, which has this simple method that is responsible for validating user credentials, emails, and password. The first thing we do is basically we do some indexing. We remove English stop words, we remove programming languages reserved words, and then we generate two bags of words or compact content descriptors of both source code files and bug reports. So you can think of them as vectors now of words, and we simply match these vectors. And vectors of source code files that are close to the bug, they get retrieved as potential candidates of buggy source code files. Now, to match these two vectors, there are so many different methods. We have vector space model, Jenson-Shannon Model, latent semantic indexing, and pointwise mutual information. So vector space model is the most basic way to do vector matching. Basically, we establish a term document matrix where each column is basically a document and then each row is a word. And the table entry is mainly the frequency of the word in that document or maybe the TF-IDF score of the word. Now, the distance between two documents, D1 and D2, is basically their cosine distance or the cosine angle between their vectors. The closer the two documents are, the closer their vectors in the space. Another more intelligent method is Jenson-Shannon Model. So Jenson-Shannon Model is a probabilistic method. So it's very similar to vector space model, but instead of building a frequency matrix, you build a probability matrix. So you have the documents in each column of the matrix, and then you have each row basically the probability of a word appearing in that document, which is calculated as the frequency of the word in the document divided by the number of words in that entire document. Then the distance or the similarity of two documents, D1 or D2, is simply calculated using this equation right here called the Jenson-Shannon divergence. H here is basically called the entropy. And you just plug in the numbers here and you can get a score between 0 and 1, basically an estimation of how related or the probability of two documents to be related. The third set of methods we consider in our analysis the information theoretic methods. Information theoretic methods depend on co-occurrence statistics. For example, if you ask any person with common sense, which is close to a computer, a banana computer or an apple computer? Well, most people would say an apple computer. Even though if you open an English dictionary, both words, banana and apple, they stand at the same distance from a computer because they're both fruits. However, because the words apple and computer appear together a lot, or they co-occur a lot, they're considered more related. So words co-occurrence can be considered as a measure of their semantic relatedness. An example here, for example, if I want to estimate the distance between computer and banana and computer and apple, I can find any text corpus. Let's assume Wikipedia. I find the number of documents or Wikipedia articles that contain the word computer. I find the number of articles that contain the word banana. Then I find the number of articles that contain both words together. The same thing for computer apple and then apple computers. And then I plug them in this simple equation right here. And then I get a number between minus infinity and infinity that would tell me how close these words are to each other. For example, in our analysis here, a banana to a computer is minus 0.67. The number is negative, which means they're not really that related. However, apple and computer, they have 17.65, which means they're really related. Now, we usually plug in that number into this normalized equation just to get a score between 0 and 1, where 0 means that two words are not related at all, and 1 means that two words are very related. So this is called the pointwise and mutual information between two words. Now, if we can't calculate the similarity between two words, we can simply calculate the similarity between two documents. Basically, we plug in the two artifacts or two documents, T1 and T2, in this equation right here. I know it's a little bit long, but I promise it's a very easy formula. Basically, for each word in T1, you calculate its most related words in T2, and they do the same thing for T2, and then you just get the average. It's going to give you a score between 0 and 1, representing how similar the information in two documents are. Now, we have all these methods. We want to compare their performance. How good are they in retrieving bugs? To conduct our analysis, we use 5 ground truth data sets. These are 5 software systems, open source systems, very popular. We have all these benchmark data sets. Each data set basically has a number of bug reports and source code files. And we know that ground truth, or we know the source code files that are actually related to each bug reports. So now we know the answer, so we simply now can plug in our IR methods and calculate or estimate the performance. So the way this analysis works, again, you have the bug reports, you have the source code, you apply basic indexing on source code, you do stemming, you remove stop words, and then you try to match source code with bug reports using the different methods, and then you measure the performance. So the way we estimate the performance is using a method called the measure called top n rank. So again, assuming I have an IR method, let's call it I, and it retrieved all these source code files in response to 3 different bug reports, 1, 2, and 3. Now here, each box represents a retrieved file. The green boxes represent true positives, and the red boxes represent false positives. Now, TR10 basically is how many times this method managed to get at least 1 true positive in the first 10 files retrieved for each bug report. So in this case, we only consider the top 10 files retrieved for each bug report. So all 3 methods managed to place at least 1 true positive in the top 10. So the score here, TR10, is 100. Now we can go TR5. So how many true positives for each bug report or how many for how many of the bug reports that information retrieval method managed to retrieve at least 1 true positive link here for 2 bug reports, so that TR5 is 67%, or you can even go TR1. So how many times the information retrieval method managed to get at least 1 true positive to be at the top of the list. In this case, it's 1 over 3. So the logic behind the TR score is that in bug localization task, identifying at least 1 buggy source file often makes it much easier for developers to find the rest. So we are really interested on which method can at least place 1 true positive file in the first 10 files that are retrieved or considered similar to the bug report. Now, we measure the performance at TR10 for all of our information retrieval methods over all of our benchmark data sets. We average the results, and here are the results over the different, again, source benchmark data sets. And you can see the information theoretic method, PMI, managed to get us the best performance. And then followed by vector space model, and we have LSI also competing. Overall, information theoretic method achieved significantly better results. And the logic or the explanation for that is that PMI favors larger files. And as we know from empirical analysis, that larger files are usually responsible for most bugs in software systems. Whenever software systems or source code files get big, they start getting buggy. That's why we need to refactor. We need to go back and apply extract class and extract method to try to make our source code files or classes smaller. All right, so now we know the results, we know the performance of each of these methods individually. Now let's talk about the hybrid approach or combining these methods. If we combine these methods together, can we gain more performance improvement? Well, the logic behind combining methods or the hybrid approach is that each method manages somehow to retrieve a unique set of true positives that other methods fail to retrieve. So for example, if you look at this table here, VSM managed to retrieve 93 unique true positives that no other methods managed to retrieve. VSM and LSI, you can see here, VSM managed to retrieve 359 unique files that LSI failed to retrieve. So if you look at this symbol diagram right here to the left, you can see how different methods retrieve different true positives. So if we combine their performance, we might be able to get more positives, all right? So again, the way this method or the hybrid IR works is the following. I have a bug report, let's call it X, and I have a source code file, let's call it Y. First, I calculate the similarity between X and Y using I, assuming here I got 0.9, and then I calculate the similarity between X and Y using J, and here I got 3%. So now I have two similarity scores. Which one should I trust? I or J? So to determine that, we basically plug in these two similarities in this simple equation here for combining the outcome of information retrieval methods. Now here, the similarity between X and Y based on the combination of I and J is lambda times the similarity between X and Y based on the I and the similarity, and 1 minus lambda times the similarity of X and Y as estimated by J. Now Y here is the confidence in the similarity. So it's a score between 0 and 1. So if I have 0.9 lambda, that means I 0.9 trust I. So I assign 0.9 confidence to I and only 10% confidence to J. Now, to calculate the optimal lambda values for our hybrid combinations, we basically follow an exhaustive search process. So for all of our systems, we run our analysis from scratch, and then we measure the analysis at different lambda values. We did this incremental steps, 0.1, 0.2, 0.3. So for example, this diagram shows when you combine VSM with other methods, you will combine VSM with PMI. So the maximum performance, or we achieve the best performance whenever we assign the lambda of 0.2 to VSM, which means PMI was assigned a lambda of 0.8, which means we trusted PMI more. So when you trust PMI more than VSM in the hybrid combination, you should get the best performance. Now we repeated this analysis for every single combination of methods in our data, in our analysis, and we arrived at these optimal values that were approximate for all the pairs. Which here, for example, if I wanna combine VSM with LSI, I can assign both of them 0.5 lambda, which means I trust them equally. However, if I assign VSM with PMI, I need to trust VSM less. I give it 0.2 confidence level, and the 0.8 go to PMI. So now once we know the optimal lambda value, we run our analysis again. And here we measure the gain in performance. How much the performance of individual methods have improved after we combine them with other methods using the optimal lambda values we were able to find. So for VSM, we can see there's a significant improvement in the performance, and the best improvement happened when VSM was combined with PMI. Keep in mind, this is just the percentage gain from the baseline or from the individual method, and how much improvement happened after it was combined with other methods. Let's go to LSI. See, there's 15% improvement or performance gain when LSI was combined with VSM. However, there was 94% improvement when LSI was combined with PMI. The same thing for GSM. And then we go to the last one, PMI. Even PMI, which is the best performing method individually, it also gained some bit of performance, or was able to retrieve more positive when it was combined by other individual or by other IR methods. So conclusions is that optimal lambda values can be calculated for hybrid IR method pairs. You can determine these optimal values using exhaustive search. The performance gain is observed for high-performing methods as well. So even if the method performs well individually, if you combine it with a less achieving method, however you manage to find the optimal lambda values, you still can maximize your gain from the combination. Information theoretic methods, PMI, are the best method individually and whenever they combine with other methods. So you have if you have a bug localization engine, for example, that relies on BSM and you want to improve its performance, just basically combine the results with PMI and you should get significant improvement in the performance. The methods, of course, that benefit the most from combination is poor performing methods. When you have a method that doesn't do well individually, combine it with an IR method like PMI that does really well individually, assign them the right optimal lambda scores, and you should get really significant gain in the performance. Now, what are the implications of this work? Well, we can build more practical bug localization engines. We can create bug localization engines that are better at determining the scope of the bug in the process. Again, in the system. Again, the point of bug localization is not exactly finding like exactly which line of code caused the bug, but it's about approximating a search space. And instead of me searching up, let's say thousands of millions of lines of code, would just give me a window to search at. So it helped me to localize my bug. This is why this is important these days. Well, take a look at the system here, the Kubernetes, which is an open source system, has more than 25,000 issues reported. For a new developer who want to contribute to this project, it's really hard to go tackle any of these problems because you have to go back and look at the code. So with IR support, hopefully we can match these open issues with the source code base and try to find the places where these errors could be fixed. So we can significantly reduce the amount of time developers spend during maintenance sessions on bug localization. And this concludes our paper. Thank you so much, and I'm open for questions.